Okay, hello people. I have good news and bad news for you today. The good news is today's lecture is pretty conceptual, so there's not going to be a lot of complicated algorithms or math or C or anything like that. It's pretty high level, so you can kind of just sit back and enjoy the topic. The bad news is it's kind of long, so we're going to have to start right now. Before we do, there are a bunch of announcements from today. There's the last homework, which is homework 7, that's due next Monday. There is a new project, the last one, it's due next Tuesday. It is, I think, shorter than the first two projects, so hopefully this week is enough for you to finish it. And then project 2 is still around, but because I think we heard from some people that they're still working on it, we'll give you till Friday to finish it. So hopefully that alleviates a bit of stress. There's a final exam next Thursday from 5 to 8 p.m. If you can't make it, there's a conflict form to fill out. And there are labs that are optional. SID's discussion has not been attended in the last couple of weeks, so we're just converting it to office hours. So if you want extra office hours, Tuesday and Thursday, 9:30 a.m. is now office hours. And just like the midterm, next week we'll have a bunch of review sections. And then I think we'll post about those on Piazza soon. And the good news is the lectures are over this Thursday. So anonymity and Tor, which comes up this Thursday, is the final lecture that is tested on the final. And next week, it's all just random fun topics that we thought of. So they're all optional. Feel free to come or not come or watch the recording later, but they're pretty fun. So I would definitely recommend giving them a look, but we won't test you on anything. So the last lecture you have to worry about for the final is this Thursday. Okay, that's a lot of announcements. So I'll let you start it for a second. Okay, but I think this is the last batch of announcements. So this is basically the plan for the rest of the whole course. Okay, so as you can see, there are a lot of topics today, so we'll just jump right in. Okay, so the kind of theme for today is detection. So far in networking and a lot of previous units, we've talked about how do we prevent attacks. So, in TCP, how do I prevent an attacker from injecting packets? Or in TLS, how do I prevent a man-in-the-middle attacker from messing with my data? Stuff like that. Those were all prevention methods, but it turns out a lot of prevention methods aren't perfect and attacks will slip through. So no matter how good you are at preventing, usually a couple of attacks will slip through. So if you recall way back in our security principles lecture, there was one principle that said, detect if you can't prevent. And that's what today is all about. So far we've had all these prevention methods, and today is like, what if we can't prevent? Well, then we should probably detect. So today is all about how do you detect network attacks when they happen? So we're not worried about stopping them. We're worried about if they did happen, is there some way for us to flag that they occurred? So before we dive into a bunch of detection methods, we're going to introduce just one last kind of bonus attack, and we'll use this attack as an example across the whole lecture. So this is not like a detection method or a system or anything. It's an actual network attack, but it's a relatively simple one. So we'll just put it here for your, I guess, just for you to learn about it. And we'll use it throughout the rest of the lecture as an example of something we're trying to detect. So here's the attack, and then the rest of our lecture is going to be, how would I try to detect something like this? So this one's called path traversal. It's also on the top, not 25, but top 17, I guess. And here it is, it's at number 12. So we've filled in almost all of this table already. I think this is maybe the last one we're going to fill in, but yeah, we've definitely seen a lot of these, and path traversal is yet another one we can show you. So this one comes from the interpretation of Unix file paths. So if you're on a Linux system or a Unix system, I think that includes like Macs and other things, a file path points to a file or a directory, which you might know as a folder. And in file paths, there are some special characters you might recognize. So the most common one is slash. If I want to go into a folder, I use slash. So I do /home/documents and so on, right? There's a couple other weird ones. So sometimes you see the one period. Then the one dot says, this is the current directory. So if you've ever run a C program, and when you run the C executable, you do ./program. What you're actually doing is you're saying dot for the current directory, and then /program to run the program. And then there's also two periods, which is for the parent directory. So you see these sometimes. They're not too common, but they can be used for attacks, as we'll see. So here's a toy file system that we made up. It starts with a home folder. The home directory has 2 folders inside a public folder and a private folder. Sorry. Cough. Okay. So there's a public and a private folder. The public folder has 2 photos inside that are files, and the private folder has a secret passwords file. So I can refer to any folder or file in my toy file system here with a file path. So for example, if I have this file path /home/public/evanbot.jpg, then what I'm doing is I'm starting at the home directory, and then the slash tells me to go into the next directory, which is public, and the slash tells me to go into the next directory. So now I'm at evanbot.jpg, and now I found a file. I can also use the dots that we saw before. So maybe we're currently in the public directory already. So if I'm in a terminal or something, I have the public directory open, and I do ./codabot.jpg. Well, what that's saying is the dot says the current directory, which is public, and then the /codabot.jpg takes me down here. So that's what this is. And here's the weird one. So let's say you have this file path /home/public/dot/private/passwords.txt. Well, if we trace this one by one, we'll start at home, and then we'll go into public folder, and then the dot says go up 1 level or go to the parent. So if we're in public, the dot says go to the parent, which takes us back to home, and then it takes us to the private and then the passwords file. So the dot always takes you up 1 level is essentially what it does. So this is something you can use for an attack, and the attack kind of goes like this. So again, consider our toy file system, and now let's say we're going to offer this file system to the user. So this front end is something for the user to type, and the user types the file name. And when the user types the file name, we plug it in. So we say /home/public/ whatever the user typed, and we give it to the user. And the idea here is that the user can only access the public files because we are adding /home/public for the user. So the user could type evanbot.jpg and they get evanbot. If they type codabot.jpg, they'll get the codabot.jpg file. Right? So we're giving the user access to just this public part, and in theory, we're not giving them access to the private part, right? If they had typed passwords.txt here, then the backend would try to send /home/public/passwords.txt, but there's no such file called /home/public/passwords.txt. So this seems secure, but there is an attack, and it's using the dot that we just saw. So if you use that dot and you're kind of clever with it, then you can form that file path that we saw earlier, which is /home/public, and then go back to home, go into private, and get the passwords file. So now, even though this website or whatever it is supposed to provide users with only the public files, some user, by using the dot to traverse directories, has access to private file. So that's why it's called path traversal, because you're traversing different paths to kind of go up and down until you find the file that you want. So that's path traversal. It's kind of similar to stuff you've seen before, like SQL injection or XSS, but in SQL injection, our problem is that things are treated as SQL code, or user input is treated as SQL code. In XSS, the problem is that user input is treated as JavaScript. Well, path traversal is the same thing, but in this case, user input is treated as a Unix file path. So it's kind of just another example of this recurring problem. And the way you would solve it is to make sure that user input is not interpreted as a file path. So the same way you would stop a SQL injection attack by making sure that the user input is not SQL, or stopping an XSS attack by making sure the user input is not JavaScript. In this case, you would double check that the user input is not a file path, or that you're not interpreting it as a file path. So that's the path traversal attack. It is kind of similar to some previous ones, which is why we kind of speed through it here. But remember, today is not about defense or prevention. So this is a good defense against file path traversal attacks, but we're not worried about defense today. We're thinking about prevention, or not prevention, sorry, detection. So today's goal is, if an attacker has done this path traversal attack, so our defense failed, or we didn't have a defense, and an attacker did this, how would we detect that the attacker performed a path traversal attack? And that's basically what all of today is about. And so just keep this in the back of your head as like an example. But again, this is not about detection. It's just an example of something we're going to try to detect. Okay, so there are several different types of detectors. So first we have to choose a type of detector. And what we mean by detector types is where does the detector go on the network? So here's a picture of a network. It has a border router, and then it has a bunch of computers inside the network. So the network can have servers that are serving web. They could have name servers for DNS, a bunch of other stuff, right? And then maybe the employees have their computers in the network, and there's a bunch of different machines all in the network. And all of the machines are connected to the internet. So the way they're connected, if you remember your local area network, is they all send packets to the router on the local network, and then the router forwards it through a bunch of hops into the rest of the internet. So this is a local area network here, and then the router is the gateway to the rest of the internet. So this is from the intro to web lecture or networking lecture a while ago. And the question we have is, if we're trying to design a detector, where does the detector go? Does it go like here? Does it go here? Does it go here? There has to be some place on the network where I'm installing this machine. And the place where I install it determines what type of detector I'm using. So the first one we're going to see is to put it here. And if you put the detector here on the router, then you've created what's called a network intrusion detection system, or NIDS. I think some people have called it NIDS, but I've always heard it as one word, NIDS. So that's what we'll call it. So the NIDS is a detector installed on the network between the local network and the rest of the internet. So everything inside the network, before it passes to the outside, or anything on the outside before it passes inside, it'll always pass through the network intrusion detection system. And what it's going to do is monitor network traffic to detect attacks. So that's the NIDS. And the way it would work is, usually what happens is the NIDS maintains a table of all the connections that are going on, and it keeps track of what's happening in every connection. So if it's a TCP connection, it'll reassemble packets and figure out what's going on. And if the NIDS sees a brand new packet that's not associated with the connection, then maybe there's a new connection that's happening, or maybe there was a connection that had already been going on before the NIDS started up. So now that the NIDS has just started up, it sees a bunch of new connections, and it'll add those to its table. So its table will always contain kind of a mapping of, well, if I get a packet, it belongs in this connection. If I get a packet and I don't know what connection it's from, I'll put it in this new category. So it'll sort out every single connection and do some analysis to figure out what's going on. And you can also be a little bit more sophisticated here. So not only can you use it to detect attacks, but you can also analyze the traffic that's going through and figure out, well, who's talking to who, or what are they talking about? So if you want to do some like network analysis to figure out what your users are doing, or what kind of traffic is your server getting, is my server busier at 9 a.m. in the morning or at 9 p.m. at night? These are all things that NIDS could answer for you if you added some extra functionality. Because again, all it's doing is maintaining connections and reading those connections and figuring out what the attacks are. Okay, so why is a NIDS good? What's so good about a NIDS? Well, the NIDS is great because it's cheap. So the number one benefit is it's really cheap, because if I have this gigantic network with hundreds of computers and servers, all I need is a single NIDS to protect everybody. So because every packet, as we saw in the diagram, goes through the border router, that means if I put the NIDS there, then every single computer on the other side is protected. So it's cheap, which is good. It's easy to scale, which is great, because let's say you have this network and it gets larger. Well, all I have to do is just give the NIDS a bit more computing power. So this is kind of linear. So it's like, if I need twice as much computing power, I'll just invest twice as much money, or I'll add twice as many cores to it or something. So the scaling is kind of nice, right? Because all I have to do is just inject this one machine with more and more power so that it can analyze more and more packets. It's very simple to manage because, again, there's just one machine. So installing it is super easy. I just do it once and I'm done. Managing it is easy because there's just one machine to keep track of. And one nice thing here is that end systems are unaffected. So any system that's on the other end, like the servers or the computers, they don't even know that the NIDS is there, or they don't care that the NIDS is there. It is offering them security, but they don't have to change their operation. So the end systems don't have to use any extra resources. They don't have to change how they're working to accommodate the NIDS. The NIDS is just doing it for them without their knowledge. So this is really good, especially if you have an existing system, right? Let's say you have just been hired to some company and it has an insecure network with a ton of computers. You don't even know how many computers there are because they're lying all over the place. Well, one thing you can do is install a single NIDS. And because you know that every computer is going through the NIDS, you have protected the whole system. So this is very good if for some reason the security was not designed in from the start and you have to add it on, you can use a NIDS. And if you think back to security principles again, the trusted computing base is the set of things that you have to trust to make sure the system is secure. Well, in this case, the only thing I have to trust to make sure that the system is secure is the NIDS. So as long as no one has compromised the NIDS, then it's correctly analyzing all my traffic for attacks. So one good thing here is you have a very small TCP. So in general, all of these kind of follow the same thing, which is that you have one single machine and it's easy to manage, easy to install, it's cheap, it doesn't affect everyone else. So having one tiny machine is very nice for all these reasons. Okay, but if NIDS are so great, then why are there other types? It's because NIDS aren't so great sometimes. And the main thing that comes up is, first of all, the network and the end host, or the detector and the end host, might be seeing packets differently. So the NIDS could interpret a packet one way while the end host interprets it a different way, so that could be a problem. And the second problem is, what if the traffic is encrypted? So let's take a look at both of these. Well, first of all, there's inconsistent interpretation. So let's say you're the NIDS and you see this packet pass by. So you see a packet that says ... /etc/password. Well, if I look at this, I'm like, this looks like a path reversal attack because I see the ... So that makes me think this is something that's probably an attack. Maybe I should tell everybody that an attack is coming in because I see this ... path reversal pattern. But what if this packet never reaches the end host, right? Like, let's say this packet has a short time to live, or at this point, it's running out of hops. So as we saw yesterday, if the packet's time to live expires and it's hopped around too often, it'll just die out and not be sent. So maybe the NID sees the packet, but the end host doesn't see this packet, so the NID's messed up. The NID said there was an attack and it alerted everybody, but there actually wasn't an attack. So it made the wrong choice here. And the problem and the reason why the NIDS made the wrong choice here is because what the NID saw doesn't match what the end system sees. And this, in this case, it's because of the TCP packet expiring. So you could have these cases where the NIDS makes the wrong decision because it's looking at different information than what the end host sees. What about this one? Well, this one looks kind of funky. I see this like %2e, blah, blah, blah. If I'm just thinking in terms of path reversal, then the thing I'm on the lookout for is the ... because I remember that ... is the path reversal attack. So when I see this, I'm like, oh, that doesn't look like a path reversal attack. I don't see any ... I just see a bunch of percents. So maybe I'll just let this through because it doesn't look like a path reversal to me. But if the NIDS thinks that, the NIDS has actually been fooled by the attacker because the attacker had been using URL percent encoding. So if you remember, URLs can have special characters, and if you want to use special characters, you have to encode them. So maybe what happened is the attacker put this in the URL, and now that the end host decrypts it or de-encodes it, if the end host decodes the URL, then what happens is this decodes to ... /etc/password. So the NIDS got fooled here. The NIDS thought it didn't have to alert because it's all a bunch of percent signs and there was no ... But it turns out this is actually ... just encoded in a different form. So again, we run into the same problem where the NIDS is interpreting something differently than the end system. And here's another one. What if the NIDS sees something crazy like this? ... That looks really strange. I have no idea what that is. Maybe it's a path reversal attack because they're accessing an illegal file. Maybe it's not a path reversal attack because this actually refers to a legitimate file. I have no idea because I don't know what the end host file system looks like. And I have no idea how the end host is going to interpret this. Is the end host going to interpret this as a path? Maybe this is just a sequence of characters, right? The NIDS has no idea how the end host is going to interpret this character sequence. So again, I run into this inconsistency where the end host is going to interpret the sequence one way, but the NIDS has no idea how it's going to happen, so it doesn't know what to do. So all of these problems lead to an attack that an attacker can do. So again, the problem is the observability isn't correct, it's imperfect. So in the time to live example, what the NIDS sees does not match what the end system sees. And the other problem is incomplete analysis. So the way that the NIDS is analyzing this packet is different than how the end host is analyzing the packet. So they're doing it two different ways, and you get this ambiguity. And both of these lead to a problem that the attacker can exploit. So if the attacker knows that the NIDS is interpreting it one way and the end host is interpreting it the other way, then what the attacker can try to do is they can craft a special structured packet so that the NIDS thinks it looks okay, no problem, but the end host thinks it looks like an attack. So that's called an evasion attack. And if you're using a NIDS with imperfect parsing, you run into something called an evasion attack. And yeah, someone said this is all assuming data is in plain text. So you're absolutely right. And I think the very next slide is going to talk about that. So far we're thinking in terms of just plain text packets. And if the packets are plain text, then stuff like this can happen. So as someone brought up I guess before we do that, let's talk quickly about defenses. So how would you stop someone from doing an evasion attack? Well, you want to fix the problem that led to evasion attacks, which is this imperfect observability or the incomplete analysis. So the way you might solve that is to say, let's make sure that the NIDS and the end host are interpreting everything the same. Now, the problem is this is kind of sort of really hard, right? Because for example, let's say I want to stop that URL encoded attack from earlier. Now the NIDS has to have extra ability to not only understand packets, but also understand URL encodings. So we have to teach the NIDS or program the NIDS to also analyze things as URL encodings. What if I wanted to stop that path reversal attack? Now I also have to teach the NIDS to parse file paths. The NIDS has to understand how Unix file paths work. And as you build on all these more and more encodings, the NIDS eventually has just so much work to do because it has to think, is this a URL encoding? Is this HTML encoding? Is this a Unix file path? And so on and so on. So this can be very, very hard to make sure that the NIDS and the end host are agreeing upon the same interpretation. You could also just set a rule and say, this server only accepts input if it's in a certain form. So for example, I say, in this server, all requests have to be URL encoded before you send it to me. And so the NIDS knows that everything coming in must be a URL encoding, and that will stop the inconsistency. So the NIDS and the server all agree that everyone will be using URL encodings, and that'll solve one problem. Or you can say everything is not URL encoded and then not parse URLs. So if you force everybody to agree upon something, then that could also solve your problem. You could also just say, I don't know which one it is, but I'll play it safe and analyze all of them. Now, this, of course, runs into the problem of it might become exponential or have just so many different possibilities that you eventually are wasting a lot of computation resources. But it could help to say, well, I know it's one of these two, but I don't know which one it is. So just to be safe, let's analyze both. So that could be something you can do as a NIDS. Or you can just flag it and say, I'm not 100% sure this is an attack, but it might be an attack, right? I see this %2e2e2e thing, and I think this could be some attacker trying to fool me. So I'm going to flag this and say, this could be an attack. And let's have a human look at it later, or let's have some other software come and analyze this later. So maybe you're not sure, and so you just flag that I'm not sure, but let's have someone else take a second look. So these are all ways you can stop evasion attacks. Okay, so back to something that someone mentioned, which is so far we've assumed that everything is not encrypted, but as we've seen, a lot of modern network traffic is encrypted. And in fact, it's encrypted so well that the NIDS is kind of out of luck. Because remember, TLS is end-to-end secure, which means everybody in between cannot read or modify traffic. So if TLS is end-to-end secure and the two ends are the server and the client, then the NIDS, who is in between those two, cannot read any of the encrypted traffic. So now what does the NIDS have to do, right? It's kind of stuck. It doesn't even know what it's reading. How is it going to detect attacks if it doesn't know what it's reading? Well, one thing you can do, and it's kind of ugly and gross, is you can say, the NIDS has access to all the private keys. So when I make a TLS connection, I also give the key to the NIDS so that the NIDS can decrypt packets and inspect them for attacks. But doesn't this just feel kind of gross? It's like TLS gave me this super nice property where everybody in between did not know what I was talking about. I had this wonderful end-to-end property. And now I'm breaking the end-to-end property by giving my private key up to someone else. Right? So that's kind of gross. And also in general, I don't want to have to give my secrets to some network machine that I've never vetted before. So that could be kind of gross, but it is one possible way around this. Okay. So as you can see, encrypted traffic, there's not really a great solution. You can either give the NIDs access, you can let the NIDs man in the middle by creating two TLS connections, as we saw, I think, yesterday. So those are all kind of solutions, but again, none of them are perfect, and you kind of run into this issue. So it is a drawback. Okay, but that's it for NIDs. So now let's talk about the other method of, or another method of detection, or another type of detection, which is putting it somewhere else. So here's the diagram from before. Again, everybody is on this side, and they talk to the internet by going through a router. So the NIDs put the detection in the router, but what if we put the detection over here on this side, which is we put them on the end hosts. And this creates something called the HIDS, which is a host-based intrusion detection system. So here, we're putting the detection on the end hosts. So the server gets its own detection system, the employee computer gets its own system, and this one also gets its own system. So what's so great about the HIDS? Well, it turns out HIDS and NIDS are kind of opposites of each other. So the things that were terrible about the NIDS are now super great on the HIDS. And the things that are super great on the HIDS are kind of terrible on the NIDS. So they're kind of opposites of each other, and which one you want to use depends on your application. So remember how we had all those inconsistency problems with NIDS that were super ugly and we didn't know how to fix them? Well, if you use a HIDS, almost all of them are completely gone because the HIDS is in the exact same place as the end host. So however the server interprets it, the HIDS will also interpret it the same way because they're the same machine. So that's super great. What about that encrypted message problem that we talked about earlier? Again, not a problem for HIDS because HIDS is working on the end host. So remember how we said end-to-end secure? Well, the HIDS is one of the ends. So it can see the encrypted messages. So these are basically the drawbacks from NIDS that are solved here. And there's some kind of extra protection that HIDS provides. So you can also use the HIDS to protect against threats that are outside of the network. So the NIDS was only expecting packets that came in, so it was only analyzing the network for threats. But the HIDS can also analyze other things, like what if there's a malicious user inside the network, or what if someone hacks into my computer and does some weird things? So the HIDS could possibly protect against those too. And the performance is maybe a little bit better depending on your application or your threat model. So if you're worried about the denial of service attacks, then using one NIDS could be a problem because remember, the NIDS goes here. So every single request has to pass through the NIDS. So it's possible that an attacker trying to do denial of service could try to overwhelm this NIDS by forcing it to compute a lot of stuff or by giving it lots of packets. And the single NIDS could be overwhelmed because it has to be responsible for every single packet. Whereas the HIDS, because they're installed on the end host, they're not as vulnerable to being overwhelmed because they only have to handle a single machine at a time. So depending on your threat model, if you're worried about DOS attacks, maybe you care more about HIDS. Great. Now the drawbacks are basically the exact opposite of NIDS. So remember, NIDS were super great because a single machine that was cheap and easy to manage could defend against the whole network. Well, the HIDS is the total opposite of that because now I need one detector for every single end host. So if my network has 300 computers, you're going to have to install 300 HIDS. And another drawback is that the evasion attacks, even though we stop most of them by installing at the end host, a couple of them are still kind of possible. So maybe, for example, if the HIDS isn't used to parsing a file system, you have to ask the HIDS or teach the HIDS how to parse Unix file names. So some attacks might still be possible depending on what privilege level the HIDS is running on. But the main drawback to me here is that it's expensive. So the NIDS is super cheap, but it had those drawbacks. The HIDS solved those drawbacks, but it's now expensive because you have to install one per end host. Okay, so that's HIDS. Now there's a third one, which is a little bit different from the first two, but it's also useful. So this one's called logging. And basically what you do here is instead of actively detecting for attacks, what you do is you say a lot of modern web servers will spit out logs. So that's kind of something that a lot of web servers do anyway. So they'll say, today at this time, someone made a request to me and I sent this request back. And later, this person made a request to me and I sent a request back. So web servers will usually keep a log of what they're doing. And this is something that most computers or most web servers will do. So what we do is we take those logs out of the computer and then we run a script on them to generate some analysis. So for example, maybe every night after the server is shut down or are no longer active, you extract the log files and then you analyze the log files to see, wait a minute, someone accessed this, computer with an attack, with a dot dot slash attack. So an attack probably happened. So that's logging. The benefit here is that it's super cheap because, like we said, most web servers already do this anyway. So basically all you're doing is like taking a Python script or something and running it on some files. That obviously is super cheap, right? I don't even have to install anything. I can just extract the logs that already exist and then run a Python script on them. So super easy. And again, the benefits of the HIS are still here because these logs come from the end hosts. So the end hosts know how they're interpreting these logs. So you are receiving the logs as interpreted by the end host. So you don't have to worry about those inconsistencies that the NIDs had to worry about. So that's great. Now the main drawback here, this is the biggest one, which is there is no real-time detection because logs only log information after it's happened, right? So if the server has logged that, user X made this request and I responded to it, that has already happened in the past. So by the time you run the script on the log to look for attacks, even if you find one, it's like, oops, too late, it happened a couple hours ago. So if you really need real-time detection, you would not ever use logging because it's only there to help you detect attacks after they happen. But there are some scenarios where you might want to detect attack after they happen, right? It would be better to detect that it happened afterwards than to not detect it at all. So maybe it's still useful. And again, there are some cases where maybe the log script needs to learn how to parse something like Unix file names. So if the log sees something like dot dot slash slash dot dot slash, right, that could be spit out by the web server. And now the script has to figure out what that dot 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 slash thing means. So again, there are some inconsistencies, but a lot fewer than something like a NIDS. And another attack that an attacker can do, which is kind of clever, is once they finish attacking, they can go to the logs and erase the evidence of the attack so that when you analyze it, you don't see that the log said there was an attack, even though it happened. So the attacker could try to hide themselves by erasing the log. Okay, so those are the three methods. I'll pause really quickly if people have questions on them. But basically, all you really have to know is for HIDs and NIDs, where it's installed, and then be able to kind of come up with some benefits and drawbacks for each one. Okay, cool. So the next thing we're going to talk about is how do we measure if our detector is good or if it's terrible. So we've picked our detector, we've installed it, and now we have to figure out, did it work? Was it good at detecting attacks? Was it terrible? Let's find out. So to do so, we have to figure out how do things go wrong. Someone asked something. Let's see. They asked, HIDs and logging are about the same when it comes to ambiguities. Yeah, I would say so. Because HIDs and logging both are working on the end host. So they both have the same view as the end host generally, but there could be a couple exceptions where maybe the end host file system is not accessible to the HIDs or the log, so that the HIDs and the log have to manually think about Unix file names. But yeah, I would say generally these two are the same in that they're both better than NIDs, because NIDs is a completely other machine that's not the end host. So it could be very inconsistent. But HIDs and logging, because they're on the same end host, are generally pretty good. But yeah, that's a good question. I think they're comparable. Okay, so back to accuracy. So the way we're going to measure accuracy is to think about what can go wrong. So remember earlier we had that problem where something was an attack, but we didn't alert because we thought it was okay. Or something wasn't an attack, but we alerted because we thought it was an attack. So in both cases, we messed up. And there are names for the ways that we mess up. So if you alert when there's no attack, that's called a false positive. When you fail to alert when there is an attack, that's called a false negative. So these are the two types of ways you can go wrong. Right? Either there is an attack or there is an attack. Is not an attack. If there is an attack and you alert, then you were right. That's great, not an error. If there was an attack but you did not alert, that's a false negative because you messed up. If there is no attack and you do not alert, then you're great because you got it right. If there is no attack but you alert, you got it wrong. That's a false positive. So that's why these are the two errors. And the way you measure the accuracy of a detector is to think about how often do I get these errors? So the false positive rate says, given the fact that there's no attack, so if I give you a bunch of non-attacks, how often do you screw up and tell me that there's an attack? And that's the false positive rate. And the false negative rate is saying, what if I give you nothing but attacks? So if I feature like 100 different attacks, how many do you not alert on? So those are the errors. And again, all we're doing here is just measuring how often do these two things occur. So we would like to have a very low false positive rate and a very low false negative rate. Right? I do not want either of these errors to happen. So I don't think you have to worry too much about the probability behind this. Just know that the false positive and false negative rates measure how often the errors occur, and the lower these are, the better. And I think that's as far as you have to know. Okay, so this slide would be a little bit more interesting if there was animation, but the idea here is, let's think about, ideally I want a perfect detector. What if I can have a detector that's completely perfect and has a false positive rate of 0? So it never ever messes up. If there is no attack, it will never ever tell me there's an attack. Well, one way to do that is just to say, whatever input you give me, I will not alert. So you give me a non-attack, I won't alert. You give me an attack, I won't alert. No matter what, I won't even look at the packet, I'll just say no. So you can give me whatever you want. I will just close my eyes and say, that's not an attack, that's not an attack, that's not an attack. And just let them all through. If you do that, you have a 0% false positive rate, because remember, false positive rate says, how often do you screw up an alert incorrectly? Well, I never alerted, so I never screwed up. Every single non-attack, I correctly classified. So I have a 0% false positive rate. And the same thing for false negatives, right? If I always say attack, so again, close my eyes and whatever they give me, I just say attack, attack, attack. Yep, that's an attack. Yep, that's an attack. No matter what they give me, then I have a 0% false negative rate, because a false negative happens if I fail to alert, but I'm alerting every single time. So of course I will never fail to alert. Right? I'm doing it no matter what. But even though these are perfect detectors, are they very useful detectors? Not really, right? They're not giving me any information because they're not even looking at the packet and doing any strategy for detection. They're just blindly saying yes or no. So this just shows you that, yeah, I can make perfect detectors, but they're going to be kind of useless, which means instead of trying to be perfect, I have to deal with imperfect detectors and deal with trade-offs between them. So I can't have a perfect detector because it'll be useless. So instead, I'm going to have a good enough detector. And how do I determine if a detector is good enough? I have to balance false positives and false negatives. So it's really, really hard to have a great detector that's like 0, 0, 0% false positive, 0% false negative, but you can have a good one. And what do we mean by good? That depends on what system you're using it on. So, how often does your system have attacks? How much does a false positive cost? How much does a false negative cost? And kind of the classic example of this is a fire alarm. So let's say you have 2 fire alarms that you can choose between. One of them has a very low false positive rate, but the false negative rate is just kind of so-so. And one of them has a very low false negative rate, which is excellent, but it has a pretty bad false positive rate. So if I'm installing a fire alarm, would I rather have a very low false positive rate or a very low false negative rate? Well, if I think about it, if I get a false positive, that means that there was no fire, but the alarm went off anyway. Well, if there's no fire and the alarm went off, everyone's annoyed. We have to step outside. The fire department has to come and take a look. And eventually everyone's like, okay, no fire. Everyone can go back inside. Well, that wasted my time, but that's not too bad compared to a false negative where there is a fire, but the fire alarm did not detect. Well, now your building is a pile of ash. So as you can imagine, the false negative is much, much, much worse than the false positive, right? You would much rather step outside and take 10 minutes to double check there's no alarm than to no longer have a building. So in the case of fire alarms, you would much rather choose the one that has the false negative rate because you do not want buildings to disappear. But this is in a certain setting, right? So maybe there's another setting where you would rather have a higher false negative rate in exchange for a low false positive rate. And we'll see one of those in just a moment. But it depends on your system. So there are lots of different detectors out there. They all have different false positive and false negative rates. And there is no one detector that is the best. There are lots of different good ones, and which one is best depends on your setting. Okay, so here's an example of one where you might think about false positive rates. And this one's kind of tricky to think about, and you have to use a lot of numbers. So let's try to just walk through it. So let's say you have a detector with a 0.1% false positive rate. That seems super good, right? You could have 1,000 non-attacks and only one of them will be wrong. So given 1,000 non-attacks, this detector will be correct 999 times. It'll be wrong just once. That seems pretty excellent to me. I would definitely use this, but let's consider where we're using it. So let's take this detector and use it on a server that receives 1,000 non-attacks and 5 attacks per day. In this server, how many false positives do I have to deal with? Well, there's 1,000 non-attacks and 0.1% of them are attacks. That's a single false positive that I have to deal with. That's pretty good. I can deal with 1 false positive per day. What if now I have a really popular server that takes 10 million non-attacks per day and just 5 attacks per day like before? Well, how many false positives do I have per day now? I have 10 million times 0.01%, which is, I have 10,000 false positives. Okay, that's a lot. And let's say your system says if there's a false positive or if the detector alerts, a human has to come and look at it and double check. Well, in the first case, that's fine. The human can just check 1 case per day and see that it's a false positive, no problem. But look here, in the second case, the human has to check 10,000 packets per day. That's a really miserable job for a human, or I have to hire a lot of different humans. So this might be a really terrible detector if I have 10 million non-attacks per day, right? And notice this was the same detector in both scenarios. So I was not changing the detector at all. All I changed was the environment that the detector was being deployed in. So this just shows you can have a detector, but the quality of it depends on where you're using it. And the other thing that this shows is accurate detection is really, really hard if the base rate of attacks is low. And by base rate, we mean how many attacks are there compared to non-attacks. So if there are only 5 attacks out of 10 million, that's really, really hard to find. And you need a detector with a very, 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 very low false positive rate to even begin to try to find them accurately. Whereas in this first case, because I didn't have so many attacks, my base rate was higher, so it was very easy to find 5 attacks. And all I had to do was just take care of a single false positive. So if there are very, very few attacks, then it's very, very hard to detect them. So in diagram form, this is kind of how it would look. So I'm using the same detector on both of them. This one takes 100 requests per day, and 5 of them are false positives. That's not a problem because I only have to deal with 5 false positives. But in this case, I have 1,000 requests. And again, the false positive rate is the same because using the same detector. So 950 things are not false positives, and 50 of them are false positives, which now I have to deal with 50 requests per day instead of 5 to manually sift through. So I didn't change the detector, right? The pie chart looks the same in terms of proportion, but because it got bigger, I have more requests to deal with. And I just realized this should say false positives in dark red and not false positives in light red. So my apologies for that. But again, the proportion is the same, but because the absolute number has increased, the detection becomes harder. So yeah. This is also related to something called the base rate fallacy. So this is kind of its own big rabbit hole of like cognitive research and statistical fallacies. So we're not going to get into that. But if you do the math from before, you basically see that if you remember the detectors from before, if I have 10,000 false positives, let's say I got 10,000 false positives, and let's say we have a 0% false negative rate. So I found all 5 attacks, and I found the 10,000 false positives. Now the detector alerts. If the detector alerts, what's the probability that it correctly alerted and gave me an attack? Well, the detector will alert 10,005 times, and 5 of them are real attacks, which gives me a 0.05% possibility that I truly found an attack. That's kind of annoying, right? Like if the fire alarm goes off and the probability of a fire is like 0.00001%, you're going to be very, very annoyed because the fire alarm is going to go off a lot. So that's kind of the scenario here, which is even though the false positive rate was so low, 0.1%, because it was, there are so many false positives, just because the detector alerted doesn't actually mean I found an attack. In fact, it actually overwhelmingly probably means I didn't find an attack. I probably found a false positive because there are so many of those. So this is called a base rate fallacy. There's a lot of statistical reasoning behind it, but the takeaway, all you have to know is that if there are very, very few attacks, then you're probably, when you try to scoop up those attacks, you're also going to scoop up lots of false positives. And now trying to find those attacks in the false positives is, again, really hard. So that's kind of the idea here. Okay. Let's talk quickly about combining detectors. So maybe instead of using a single detector, I have 2 detectors and I like them both. And I want to combine them to make a better detector. So there's 2 ways you can do this. One's called parallel, one's called series. If you've ever seen a circuit before, you might recognize parallel and series. So in parallel, what we say is if either detector alerts, we alert. So either detector A alerts or detector B or both, as long as anybody has alerted, I will alert in my combination. Now, the intuition here is that if I'm letting either detector alert, I'm probably going to get more alerts, right? Because I'm like kind of getting the combination of two sets of alerts. So I'll probably get more alerts. What does that mean? If I get more alerts, I'm going to get more false positives, right? More alerts means more of them are probably also incorrect alerts. So there's more false positives. But that also reduces false negatives because I'm catching more things as they come in. So the probability that I miss attack is lower because either A got it or B got it or both, right? So I have kind of two chances to get the attack. So the false negative rate goes down, but the false positive rate goes up. What about the series version? Well, the series version says alert only if both detectors alert. So if only one of the two detectors alert, I do not alert in my combination. But if both detectors go off, then my combination will also go off. Now, this creates fewer alerts because I only alert when both of them alert. So I'm looking for kind of a subset, the intersection of the two alerts. I could have drawn some Venn diagrams and showed you union and intersection, but oh well. But yeah, so the intuition here is that because I'm waiting for both detectors to alert, the alerts are going to come less often because if only one of them alerts, it's not going to show up. I need both of them to go off for the alert to show up. Well, if I'm generating fewer alerts, then I'm also going to have fewer false positives because I mess up fewer times, right? So the alerts only come if both of them alert. So if I have fewer alerts, then fewer of them will be wrong alerts, so I'll have fewer false positives. But now I'm going to have more false negatives because I might miss stuff, right? If I'm generating fewer alerts, then I'm probably missing more attacks that maybe one of them found, but the other one didn't find. I'll miss those. So I have a higher false negative rate. And the idea here, as with all detectors, is there's no free lunch. So you can't have a perfect detector that has 0%, 0%. You're going to make mistakes, and there usually is kind of a trade-off. So if you want to make your false negative rate lower and improve that, you're probably going to have to deal with a higher false positive rate. And likewise, if you want to get your false positive rate down, you're probably going to have to deal with more false negatives. So you have to pick your trade-offs very carefully and think about what environment am I using this detector in? And based on the environment and the base rate of attacks and how much the false positive and false negative cost, you'll pick a trade-off that works for you. And this is very, very tricky. And I think one of the slides said it's an art. So you have to perfect the art of choosing a very good detector. Okay, I think that's it for detectors. And we're moving on to styles, but I guess we can take a 5-ish minute, like a 3-ish minute break if we come back. So should we come back at 4:31, 4:32, since it just became 4:29? Okay, let's do that. Keep it going. Okay, back to styles of detection. So far, we talked about types of detectors. So we talked about where do we put the detector? What is it looking for? Like, where is it looking? So is it looking at the network? Is it looking at the end host? Is it looking at the logs? So we talked about the types, and we talked about the errors, which are how the detector can go wrong. But we haven't actually talked about how the detector finds attacks yet, right? What strategy is this detector going to use to figure out if there was an attack or not? So that's the next section, which is the styles of detection. So I don't know why they're called types and styles. I don't think that's like terribly intuitive, and I wouldn't worry about it too much, but there's kind of two things you can choose here. So you can choose the type, so figure out where the detector is, and then choose a style or a combination of styles, which is how is the detector scanning data to figure out attacks. And these two are kind of mutually exclusive. So I can use a NIDS and then use one style of attack, or I can detection, or I can use a HIDS and use that same style or something. So it's up to you. Okay, so there are 4 main types, and we're going to look at all of them and think about what's good about them, what's bad about them, why would you use it, why would you not use it. Okay. So we'll start with something called signature-based detection. So this works as in I will look at the activity, and if it matches something that I know is an attack, I will flag. So this is something called blacklisting, which is I keep a list of patterns that are not allowed. So I keep this list of like, this is an attack, this is an attack, this is an attack, this is an attack. And if I see something on this list, I alert and I say, this is something from my list of attacks, so I'm going to alert. So that's blacklisting. I keep a list of things that are not allowed. And what the signature is kind of depends on what attack you're looking for. So you can put signatures in, there could be signatures in the TCP IP header fields. There could be a signature in the URL. There could be a signature in the HTTP request. And it depends, again, on what kind of attack you're looking for. So the signature can be anything in the packet, right? Any pattern that you see in the packet, But as long as you keep that pattern in mind or in your blacklist, and when you see that pattern, you alert, then that's what's called signature-based detection. So we have a bunch of examples. Let's go back to that example from before, which is how would I find a path traversal attack? Well, if you think about it, we know that the ... is often used in path traversal because we're trying to go up directories. So I know that this is a very common signature or a very common pattern that shows up in path traversals. So let's add this ... to our blacklist. And let's say if any request has this ... in it, we'll alert and say that's an attack. We can also think back, if you remember buffer overflows, we can try to detect those as well. So we know that buffer overflows usually contain shellcode, right? And maybe there are some really common examples of shellcode out there. So what we can do is we can keep a blacklist of common shellcodes. And if any of the requests contain the common shellcode, then we'll alert and say, hold on, this is probably an attack because it contains shellcode that I know has been used in previous attacks before. So if I keep this list and I alert when I see something on the list, then that's signature-based detection. So the idea kind of is like this attack leaves a signature, it leaves a pattern that's noticeable. So if I know the pattern and I detect on it, then I am detecting attacks. Okay. So what's good about this? Well, it's very simple because all I have to do is keep a list, and if I see something on the list, I detect. That's nice and simple. It's very, very good at detecting known attacks because if I know an attack exists and I've analyzed the attack before, then all I have to do is figure out what the pattern is, put the pattern into my detector, and my detector will always detect copies of that attack. So if I know that all the path traversals use ... and I put ... in the detector, then this known attack, this path traversal attack, will usually be detected. So that's good. And in fact, what you can do is you don't have to write the blacklist yourself. You can borrow blacklists from a bunch of other people. So the security community has kind of gotten together and created lots of shared lists of common attacks. So there are these gigantic blacklists out there of all these common attacks that people have seen over the years. And you can download those and use those yourself in your own detector. So you can pool your resources and think together. So you don't have to write your own blacklists. But what's bad about this? Well, it's not going to catch a new attack without a known signature. So if someone has figured out a new type of attack, like if a buffer overflow is being detected on a couple common shellcodes, and an attacker has come up with a brand new type of shellcode, we're not going to catch that because it doesn't match any of our known attacks. So signature-based is great for known attacks, but terrible for new attacks because it has no idea what the signature or what the pattern of the new attack is. And it also might not catch variants of known attacks. So attacks could be varied. Maybe the shellcode has a couple of bytes swapped or something. And if you are not aware of the variant, or if the variant no longer matches the pattern that you're looking for, then the variant could also slip through. And the attacker could actually intentionally do this. So the attacker knows that you're using signature-based detection and that you're looking for this signature, then they can modify their attack to avoid your signature. And I think we're going to see this a lot in tomorrow's lecture about malware. Okay. And if your signature-based detection is too simple, maybe you're not looking enough for patterns. So maybe the pattern is very complicated and it says an attack is happening if the header has this and the HTTP payload has this. So you have to look very carefully at different layers maybe to find an attack. But if your signature is too simple and you're just looking at like, let me just string match or something, then it's possible that you miss variants or you miss or you make a lot of false positives because your pattern is poor. So you have to be very careful about how you choose your pattern and make sure that your pattern matches attacks, but your pattern doesn't match non-attacks, because if your pattern is not clear and it's vague and a lot of legitimate packets also match your pattern, then now you're flagging tons of false positives and you don't have a very good signature. So you have to be a little bit careful how you're writing your signature as well. Okay, that's the first one. Now let's talk about specification-based. This is kind of the opposite of the first one. So in the first one, we said, this is not allowed. If you see something that's not allowed, alert. Now in this case, we're doing the opposite, which is to say, this is allowed. So here's a list of what's allowed. If anything else shows up besides what's allowed, just flag it. And that is specification-based. So I specify what's allowed and everything else flags. And this is called whitelisting because I'm keeping a whitelist of what is allowed and everything else is alerted. So this one is kind of like default deny because I'm denying everything that's on the whitelist, and signature based is kind of like default allow because I'm allowing everything except what's on the blacklist. So in this case, I specify what's allowed and then everything else is alerted. Okay, so let's try to use specification-based detection to catch path traversal again. So let's say we have a folder and we know that everything in this folder only has file names with the A to Z, lowercase a to Z, uppercase, or 0 through 9. So we have evanbot, codabot, evanbot2, whatever, right? All the file names we know only have letters and numbers inside. Well, then we can specify this in our detector and we can say, I know that when the user requests a file, they are only going to request input that is alphanumeric characters, or they should only be requesting inputs that are letters and numbers. That also lets the detector know everything else is an attack. So if the attacker tries to do ... well, guess what? Dots and slashes are not alphanumeric characters. So that's a sign to the attacker or to the detector that an attack is going on. So I keep a list of what's allowed, and because the attacks are not inside the category of what's allowed, I detect those. Okay. So the path traversal attack will be flagged because it's not a letters or numbers. Now let's write on buffer overflows. So maybe I wrote a program that says, what's the user's age? And the user has to enter their age. Well, I know that at least on Earth, with humans, ages are numbers. So hopefully when I ask the user, how old are you? They type a number and they don't type 20 bytes of garbage plus shellcode plus RIP or whatever, right? That would not be an age. So if I know the ages are numbers, then I specify to the detector, I say, this user should only be inputting numbers. And the detector will say, okay, so, I'll only take numbers. So anything that's not a number will be flagged. So if the attacker tries to put in something like shellcode, well, shellcode is not numbers. It's not 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a bunch of random bytes. So the detector will flag that and say that's an attack. Okay, so what's good about specification? This solves a problem from signature-based, which is even if it's an attack that's brand new and we've never seen it before, specification-based will catch it because even though we've never seen it before, it's not in our list of allowed things. So if it's not in our list of allowed things, it will be flagged. So it'll flag attacks that we haven't seen before. That's nice. And if we're very careful about specifying what's allowed, we can have a very low false positive rate, right? Because if we say, we list out, these are all the things that are allowed. I only allow ages, or I only allow users to enter these files. I'm very specific about what's allowed. That means that everything else must not be allowed. And if something is flagged, it must be disallowed because it wasn't in my specification, because I completely specified everything that's allowed. So I have a very low false positive rate. Now, what's bad about this is the main thing is it just takes a lot of work, right? Notice how in these previous two, I had to manually specify that in path traversal attacks, in my web server, I only allow alphanumeric characters, or in my age, I only allow numbers. Someone who wrote the program had to manually specify this. So it's not like signature-based detection where you can just copy a long blacklist from the security community and just use it. In this case, you have to manually specify for your specific program what is and isn't allowed. And maybe your program changes over time and suddenly, in the future, ages can now have numbers. Okay, well now you have, or ages can have letters, or maybe ages can have question marks inside. Okay, well now I have to go and update that ages can have question marks, and I have to update those. And if I don't, then my detector will become very poor. So this is great if you can have the time to write your specifications, but if not, then this might not work because it takes too long. Okay, so specification is good, but it takes forever. So let's try to solve that problem. And to do so, we'll use something called anomaly-based detection. So here's the idea. The idea is I don't want to have to specify everything that's allowed so that the specification base works. I'm just going to think about, well, attacks look unusual. This is kind of true, right? Shellcode looks kind of strange and funny. XSS, which has those JavaScript tags, looks kind of funny. SQL injection, which has all those colons and semicolons, these all look kind of funny, right? They don't look like things that normal users would input. They look like things that attackers would be inputting. So maybe I can use some sort of machine learning or some sort of algorithm to automatically kind of develop a model of, I think normal activity looks like this. So maybe I take a lot of old activity that people have been doing and I analyze those to see what are some patterns of what people have been inputting. And that gives me a model. And then any activity that's different from this model, I'll learn on it. So it's basically just specification, but instead of manually saying what's allowed, you're going to try to automatically learn what's allowed by looking at past behavior or looking at some sort of database. So this is kind of tricky, but if you do it right, it might work, and we'll see some examples. So let's say you're trying to, let's say you're trying to detect path traversal attacks with anomaly-based detection. Well, in this case, I'm not going to manually specify that dot appears in attacks. I'm going to let my machine learning algorithm or my neural network or whatever look at all the past requests and realize that, hey, wait a minute, I noticed that this dot only appears in attacks and regular people never type the dot. So this algorithm that you've come up with has automatically learned this model of dot is probably something that's an attack. So you didn't have to manually specify that. The algorithm did it for you. And if that's true, then the strategy will be to alert if any request contains dot. And this is not a rule that you have to write down yourself. It's something that the program figured out for you. Well, what about buffer overflows? Maybe you look at a bunch of past inputs to a C program, and you realize that users who are not attackers, they type things on a keyboard, right? They type letters, they type symbols, they type capital letters, numbers. But these are all things that you can enter on a keyboard. So the model realizes that, well, these are the keyboard things, and those are allowed. And the things that are not typable on a keyboard, like raw bytes of shellcode, those tend to correspond to attacks. So maybe your smart machine learning neural net algorithm learned this by itself, and now it knows that if the input doesn't have human typable characters on a keyboard, probably is a good time to alert. Right? And that would work if the attacker was inputting shellcode, because shellcode can't be typed on the keyboard. Okay. So what's good about this? Well, this is great because, again, it has the same property as specification, which is it can detect brand new attacks because I am specifying or learning what's allowed and everything else is not allowed. So I can detect brand new attacks just like before. But what's the drawback here, right? This seems too good to be true, right? Why would this, why would we not just always use anomaly-based? Well, there are a couple problems, right? If your model is poor, so if you have a very bad model of what's going on, you could actually fail to detect known attacks. Maybe your model has not successfully figured out that dot is path traversal or shellcode is buffer overflow. If your model didn't figure that out, then not only have you failed to detect new attacks, but maybe you're also failing to detect existing attacks. So that's bad. Right? And again, you can also fail new attacks if they don't look unusual to our model. So maybe the attacker came up with something that looks kind of normal, but is an attack, and to the model, it's going to look all fine, even though it's not. And this could happen if your model is trained on bad data, for example. So maybe you're using your model to train it on past data, but your past data is full of attacks. So now the model thinks that all those attacks from your past data are normal, even though they're not, right? So if your model is poor or it came from poor data and it's biased in some form, then this is not going to work well. You could also have the problem of adjusting. How do you tell if something is unusual or not, right? Let's say I only allow things that are, let me think. I guess only if we only allow things that are a little bit unusual, then I can have a lot of false positives. So if I say anything that's a little bit unusual, I'll just alert. That could come up a lot because maybe a lot of users give you weird inputs, like they have typos or some kid visits your website who's like 2 years old and they keyboard mash. That could look weird and it's a false positive, right? But maybe you say, well, I don't want to have all these false positives, so I'm only going to flag the most unusual inputs, right? In the previous case, I was flagging anything a little bit unusual and that gave me lots of false positives. Maybe I'll reduce those by flagging only the weirdest, just most bizarre inputs. If I do that, the false negative rate will increase because now I'm going to miss attacks that are only slightly unusual. So I have to trade off again, just like before. What is my false positive rate? What can I tolerate? What should I want given my environment? All of this basically comes down to anomaly-based is super good. If you're going to go into security research and you want to write a paper, I recommend finding a new way to find anomaly-based detection. So this is, I think it's still a hot field of research. People are still trying to figure out smarter ways to find attacks. So if you have an attack like buffer overflows that you really want to detect, and you figure out a machine learning algorithm that gives you a relatively good detector, then you can write a paper and get your name published and win all the awards. But for now, this is still mostly a research topic, and I don't think any detectors have been built to be strong enough to be used in practice. So we're working on it, but for nowadays, if you want to deal anomaly-based, you probably just want to go into research and write a paper about it. Okay, so the last one is behavioral. So this is a little bit different from the rest. So In all the other styles, we were looking at the input, right? So I looked at the dot dot slash or the shellcode where I was looking at what came in and figuring out if that was an attack or not. Behavioral detection is different because we're not looking at the input. We're going to look at what the input does. And if the input has done some action that looks like compromise or has left some evidence of compromise, then we're going to alert. So we're no longer looking at the input. We're looking at the result of the input or the behavior. That's why this is called behavioral detection. And this can also be analyzed with blacklist or whitelist or normal behavior. So it's up to you. Sorry. Okay, I have another day of this or another 2 days of this. How am I going to survive? Okay, so behaviors can be analyzed with blacklist. You can say, here are the things that are not allowed. And if this input triggers this behavior, then I'm going to alert. Or you can say, here's the allowed behavior. If the input triggers any other behavior, I'll alert. Or I can use anomaly based if I feel like writing a research paper. So the behavior itself can also be analyzed with the previous tools, but the general theme of this detection style is I'm no longer looking at the input, but I'm looking at what the input does. So what are some examples? Well, maybe there's a path reversal attack from before. And now instead of looking at the actual path that's being inputted, I'm going to ignore that. And I'm going to think about the result of the input. So if the input came in and it caused a secret file like the passwords file to show and be accessed, right? That's a behavior that a normal input would never have, but an attack would. So I would alert this because it seems like some unexpected behavior is happening. What about buffer overflows? Well, I can look at the program as calling functions that I don't expect it to call. So one common strategy here is called syscall or system call monitoring. So I monitor the calls to the operating system. So those C library functions that call operating system calls. And I look for unusual behavior. So maybe a C programmer wrote a code snippet that never calls exec. If you look at the code, it never calls exec. And they run this program and they study what this program is doing, and suddenly it starts executing exec. And you're like, wait, what? My program I never wrote exec into this program. So how is it running exec? And probably someone has done a buffer overflow and started running exec as well. So you're monitoring the system calls and you're realizing my code never was supposed to do this behavior, but suddenly it's doing this behavior, so I'm going to flag. So in this first case, it was a blacklist, right? I said this password file should not ever be accessed. So if someone accesses it, that behavior is an attack behavior. So that's a blacklist. And the second one I'm saying is a whitelist. So it's like, well, I guess the second one's a blacklist too, right? It's like, well, saying the exec function is something that's never supposed to happen. So if it does happen, then that would be an attack. So yeah, I guess this one's a blacklist. Or you can say, my C program only calls fread and fwrite and fclose. So I know that it only calls these three things. That's a whitelist. And exec is not part of this whitelist, so I flag. So I guess it can be both depending on how you're flagging, but the idea is the same. And so what's good about this? Well, again, this can help us detect new attacks because I no longer care how the attack is being carried out. All I care about is the result. So if a brand new attack still leads to the result of compromising a passwords file, I'm still going to detect that. If I'm looking for behavior that's relatively rare or impossible in normal programs, then I can have very low false positive rates. So in the system call example, if I know for a fact that my program will never ever execute exec, and the program starts executing exec, that's basically guaranteed to be an attack. That's not a false positive, right? Because your program is never going to do that. So that would be a case where you have very low, maybe even zero false positives. This can also be cheap because a lot of existing tools already do this for you. So maybe your file system is already monitoring accesses, or your C program is already monitoring system calls. So a lot of existing tools can be used to implement behavioral detection. So you don't have to write your own blacklist or whitelist. You could just use existing tools to monitor. What's bad about this is some things could be done by legitimate attackers. Maybe the legitimate, there's no such thing as a legitimate attacker. I'm losing my mind. But a legitimate user or a legitimate process could also access the passwords file. So maybe it's hard for you to tell, was this passwords file accessed from a legitimate user or was it from an attacker? That could be hard to tell. This has the same problem as logging, which is by the time you figured it out, the exec program is already running or the passwords file has already been accessed. So it's possible that the damage has already been done. And it's possible that you want to detect attacks that have failed, but in behavioral, you only find the attack if it succeeds and has performed the behavior that's bad. So maybe you also want to find, this shellcode didn't work, but they tried it, so I want to learn about that. So that wouldn't work if you're using behavior. Okay, and just like before, the attacker can modify their attack to avoid triggering some behavior if they're very careful. So instead of using exec, they can use some other function that won't be flagged. Okay, so those are the 4 styles. I am running very short on time, but I'm almost done. So let's just kind of give you a kind of sneak preview of the rest of the world of intrusion detection. So there's lots of different strategies that are not the ones we've talked about. So we'll just kind of give you a sneak preview into them really quickly. There's one called vulnerability scanning. I think we've seen this in the buffer overflow lecture, but basically what you do is use a tool that attacks your system. And if the attacks work, then you fix them. So you see that a lot. You attack your own system and then fix it if the attacks work. That's great if you have a good scanning tool. It'll find vulnerabilities. It's proactive, which means you are preventing attacks before they happen. So that's really good. Not only are you detecting attacks, but you're also going to prevent them because you're testing your own system beforehand. So that's great. And one kind of side benefit is if you know you fixed an attack and the intrusion detection system alerts, then it's probably a false positive. So you can reason more smartly if you've done additional scanning. This takes a lot of work though, which is the main drawback. If you can't fix your code, then that's not very helpful either. It also might be dangerous if your code is sensitive. So if you run this attack suite and one of them works, it just destroys your system. That could be dangerous. So you have to be careful. Okay, let's talk about honeypots. These are fun, so I want to talk about them. A honeypot is a way to lure attackers into your system and trick them into giving themselves up. So a honeypot is a sacrificial system on your system. It has no purpose. Nobody will ever access this thing. It's never used for anything. It's not doing any real computation. What does that mean? That means if anyone does access it, they have to be an attacker because real people or legit people are never accessing the honeypot. So this honeypot is just sitting here to fool attackers or to convince attackers to access it. And if they do access it, then we know that they must be an attacker. There are some false positives here, which is that maybe your legitimate system messed up or some curious user wanted to see what was going on and they accidentally fell into the honeypot. So that could happen, but those are a little bit rare. Now, you've seen honeypots before, which is why this is kind of cool. They were stack canaries, right? Remember how stack canaries were also a sacrificial value on the stack? Nobody actually used it. So if it got changed, it must have been an attacker changing it. So a stack canary is kind of a honeypot, which is, it's kind of cool that the first lecture has linked all the way back here. Okay, so a stack canary is a honeypot. An example in the real world of honeypot is a hospital. So in hospitals, they want to make sure that employees like doctors and nurses don't read patient records because that's confidential. So what does the hospital do? They go into the computer and they enter a secret record or a public record with a celebrity name. So they're like, the president of the United States has this health information. Click here to find out how the president of the United States is doing. Is Joe Biden dying right now? Find out now. And so they have the celebrity name and everyone wants to click on it, right? And if someone clicks on it, then they fell into the honeypot because that's a fake record. And so the staff member will be caught. Another kind of computer system related honeypot is a Bitcoin wallet. So people love to steal Bitcoin because Bitcoin is money and people like to steal money. So one very good honeypot on your system is you put a computer in your system. It doesn't do anything. No one's supposed to access it. And you put a little bit of money on it. So you put like $10 of Bitcoin on it. Right? And what happens is if someone goes into your system and wants to attack you, what's the first thing they're going to go to? They're going to go to the money, right? There's a lot of different things going on, but if they look around and they see this computer that has money on it, they're going to go get the money. So if the money is stolen, that tells you that your whole system is under attack and you had better clean stuff up. So that one's kind of clever, right? And again, you are sacrificing like $10 or $20 to convince the attacker to steal your money. But once they do, you might be protecting some other really valuable information. And you know that you found the attacker, so it could be valuable. And there's also a spam trap. So you can say, let's have a fake email address that's never used for real emails. So I create an email address. I never ask people to give me email. I never publish this email address. Maybe I publish it, but this email address is never used by legitimate people, which means if someone sends an email, that's spam. So that's a very good way to catch spam because spam is being sent to people without their consent. So if I have a blank, never used email address and a bunch of spam goes to it, I have caught all of these spam addresses. So that's a good way to catch spam. So what's good about this? I can detect brand new attacks as before. Right? The attacker can do whatever they want, but as long as they fall into the honeypot, I found them. I can analyze what the attacker is doing, which is super great because if as the attacker is kind of sniffing around the honeypot and stealing my Bitcoin or sending spam, I can figure out things like who are they? Like what is the address, email address of the spam account? Where are they from? Like, where are they sending these packets from? What are they trying to do? Are they trying this attack? Are they trying this brand new attack? I can learn about the attacker without them knowing that I'm learning about them. So it's very, very tricky. Right? I can also distract the attacker, right? So in the case of Bitcoin, I say, here's free money. And so the attacker will immediately go to the free money, ignoring the more expensive targets. So that could stop some attacks as well. Now, this is a little bit hard if I have to trick the attacker into accessing the honeypot, right? I have to bribe them with some money, or if the attacker is smarter, I have to convince them that this is the real root valuable system to attack. So I have to give the attacker incentive to go there, which can be tricky. And I have to design that, and that can take some work to build it and make it convincing, right? If the honeypot is very obviously fake, then the attacker is not going to go there. So you have to make it convincing. Now, these drawbacks are a little bit less relevant in cases like the spam trap because those spam traps are aimed to catch automatic attacks. So you don't even have to convince them. They'll just send it to you anyway. So no problem. Okay. This was really quick. Is forensics. Basically, you analyze what happened. So after an attack happens, you want to go back and figure out what happened, right? So it's kind of like those detectives in those old school novels, right? The first page of the novel is always like, it's a rainy day in San Francisco, whatever. And some body is laying down on the ground. And so the detective comes in and tries to solve the crime and figure out what happened, right? So that's what forensics is you try to solve the crime and figure out the attack has happened already, damage is done, but what happened? Like, why did they get in? How do I protect my system in the future? That's all called forensics. And it's definitely important to not only detect, but also if you fail, you need to figure out what went wrong to fix your system. So that's forensics. One idea is like, if intrusion detection systems are so good, can I prevent? And yes, I can. That's called an intrusion prevention system. So not only do you detect, but you also prevent at the same time. There are some drawbacks. It's kind of hard if you're only passive monitoring, right? Most detection systems only read packets, but if you want to prevent, you may also have to actively inject stuff to stop the attacks. So that can be hard. Yeah, okay. There's a silly slide, we can talk about it later, but it's not that silly. There are some attacks you can do on this, right? You can DOS the intrusion detection system, so that's a problem. Okay, yeah, so the intrusion detection system is also a system like any other system on the computer, so it can be DOSed, it can be attacked, so you have to be very careful about that. We'll skip this. This just shows you a modern state-of-the-art NIDS and what it would look like. This is a modern HIDS, that's what it would look like. And now we're at the summary. So sorry, this definitely ended up being long. If you do have to go, we'll respect your time, but I will just run through the summary since we have some people here. So the first thing we talked about today was path traversal. And this was just a side attack to help us kind of motivate the rest of the lecture. And this attack just says, if I have some files, or if I'm letting the user choose a file path, I have to be careful that the user can't do things like .. to kind of work their way around my directories and access files that they're not supposed to access. The problem here was that the user input was being treated as a file path, just like how SQL injection has SQL being treated as code, or how XSS has JavaScript being treated. Sorry, SQL injection has user input being treated as SQL, or XSS has user input being treated as JavaScript. So that's the vulnerability, and the defense is to make sure that the user input is not interpreted as a file path, unless you wanted to. Then we talked about there are three types of detectors. There's the NIDS. This is on the network, which is good because it's a single machine. It's very cheap, scalable, easy to manage, and has a small TCV. The drawbacks here are there are inconsistent interpretations. So what the NIDS sees isn't necessarily what the end host sees, or what the NIDS thinks is going on isn't necessarily what the end host thinks is going on. And NIDS are very hard if your traffic is encrypted because now you have to give them your private key or something. That's hard. The HIDS is installed on the end host, it's host-based. Now this solves the NIDS problems because I don't have as many inconsistencies because the end host is the one holding the detection system. It does work on encrypted traffic, it works inside the network, and I have scalable performance. The problem is it's expensive because I have to install one system per machine, and there are still some division attacks here. The final method was logging, so we analyzed the logs generated by the servers. This has the benefit of being cheap and having not many inconsistencies. And this is cheap because I just have to run a script on the server's logs that have already been generated. And the drawback is that these only detect attacks after they happen. So if you care about real-time detection, then do not use logs. Then we talked about detection accuracy. So we talked about false positives, false negatives. The accuracy is how often these things occur. designing a good detector involves trade-offs. So not only do you have to pick a detector, but you also have to think about what environment am I using this detector in? So like, is it a fire alarm system? Is it a attack detection system? How costly is a false positive? How costly is a false negative? How often do attacks occur? Those are all things I have to think about. If there are very few attacks, then it's very hard to find the attacks, because as I scoop up a bunch of attacks, I'm going to have a lot of false positives, and I have to get rid of those too. Detectors can be combined, but you have to be careful, because if you do it in parallel, you lower the false negatives but increase false positives. If you do it in series, you lower the false positives but increase the false negatives. So you have to be very careful there. Then we talked about the 4 styles. So signature-based is the blacklisting one. Tell us what's not allowed. If it's not allowed, I'll flag. It's good for known attacks, but very bad for unknown attacks. Specification-based says, here's what's allowed. If anything else, just flag it. This is good for unknown attacks, but you have to write the specifications yourself, which kind of sucks. Anomaly-based says, what if I don't want to write the specifications? What if I want to develop the model with machine learning and something fancy? Well, that might work, but you have to realize that it's mostly a research paper topic, so be careful. And then behavioral says, instead of looking for the input and what the input says, let's think about what the input does and what the result of the input is. So look for evidence of compromise. The problem is this sometimes only detects after the compromise has happened, so be careful. And then we talked about vulnerability scanning, so attack your own system. We talked about honeypot, which is have a sacrificial system and see if someone steals your Bitcoin. We have forensics, which is be a detective and figure out what happened after the attack. And we have prevention systems, which prevent attacks in addition to detecting. And we finally made it. I think this is definitely going to come up as the longest lecture of the semester, but we made it. We had to go a little bit fast. Hopefully it was all relatively conceptual. So if anything was too fast, you can always go back and read the slides or the textbook and get a better idea. Any last questions before we sign off? Quick question. The due date of the project should be updated on Gradescope. Yes, let's update the due date on Gradescope, and we'll do that after the lecture. Good question. Okay, if there's nothing else, I don't want to keep you any longer, so we'll see you tomorrow for hopefully a shorter lecture.